So what we are presenting today is particularly for automotive applications, a suite of testing tools that's called MxSuite, manufactured by Denlo, of which Mike McCormack is the Director of Product Development. I'm Michael Johnson. The presentations will be mainly made by Mike. And for you who do not know much about know-how, I just want to say 3 words about us. We're focused on embedded design and development. We have about 2,000 customers in the Nordic that has been able to improve their software development process thanks to the technologies that we provide. Much of the focus we have today is on functional safety and embedded security. And very many of my customers, when I ask them, what area do you primarily want to improve? They answer, well, we want to improve and automate our testing because the testing and quality assurance process and the strains we have there is killing us. Especially when we need to prove to regulatory bodies that our process is okay. And at NOAA, we believe that every software developer deserves great tools and great support. That's very briefly about what we do, and I leave to you, Mike, to continue and tell us everything about MxSuite. I want to say, though, before I make you presenter, that we will record this. We'll record this event, and we will also welcome questions. But to use, if you want to place some questions, please use the chat window to the right, below, to the right in the communication channel, the panel we have. So we'll try to have a Q&A at the end. Okay. So Mike, I made you the presenter. You need to share your screen using the middle top button. Exactly.
All right. Good morning, or good afternoon to you and everyone. So I've been working with this tool now for since it started, which is about 12 years or so. And from the start, it's always been for assisting in developing and testing embedded. Just 1 second. So primarily, initially, it started with fully embedded systems with no user interface, and primarily used in the automotive industry. I'm based in Detroit, and you know, as the controllers in vehicles got more interactive with the user interfaces and touch screens and that kind of thing, then so the tool evolved to cover you know, the ability to touch buttons and recognize what's happening on the screen and maybe deal with voices and that kind of thing, text to speech and speech to text. But I'll start off with a traditional style embedded controller and kind of give you an idea of what the tool looks like and how we can test the system. So one thing early on in the development of the tool is we tried to abstract the test tool away from the system we're testing, so that we could switch in and out different systems. You know, if you ever use Simulink, their test tools, you'd use them for testing Simulink models, but you wouldn't use them for testing anything else. If you ever use something like Test Stand from National Instruments, you know, it's good for testing hardware systems, but you'd never use it for testing Simulink models, for example. And again, you know, if you one tool that would work on one piece of hardware typically doesn't work on another piece of hardware. So one thing we did early on was try to make it so that the same test tool could be used in any environment. So, you know, the thing I'm testing on that I'll show you I'm testing in a few minutes on my screen is some software, C code. We call it the environment, we call our virtual microcontroller. So we have something that behaves like a microcontroller. It runs on the PC, and it allows us to test you know, fully embedded code in a PC environment. In a couple of weeks, there's another presentation where we say, you know, essentially present the case that, well, it isn't sufficient to test code on a PC. We really want to test our code on the target microcontroller, and that solution is also there. And one of my colleagues then will be demonstrating that in a couple of weeks, and I'll show you how the same environment can be used for testing both on a PC, or testing a Simulink model, or testing on some piece of hardware, or even a full, you know, full rack-mounted hardware test system. But for now, irrespective of what the system we're testing looks like, I'm going to show you how the test cases look. So we'll keep it simple to start with, and we'll say this here is a test case. We'll just look at these black signals here are stimuli inputs to my system I'm testing, and the blue signals are outputs. And up here we've got a signal dictionary, and this represents all the signals that we have available from the system we're testing. And you know, often this can be hundreds, thousands of signals. So this is a small system. You know, we can see that some of them are output, we call them response signals. Some of them are inputs, stimuli signals, and then they have different types. We call them discrete for, you know, Boolean signals or state machine variables. We've got continuous signals, which are like temperature or pressure, or continuously variable real numbers. And then everything else in general falls into what we call the message, which is going to be a buffer of data, and it may be like a bus message like can or lin or something, or it may be some other buffer of data like image data, or it might be even you know, a string of text that we expect the system to speak to us, and we're looking for this piece of information, and we're going to compare what it says with the expected message. So and I can show you how we populate the signal dictionary, and we'll come to that. But for now, assume as you can see, then we have a populated signal dictionary, which are all the inputs and outputs of my system, and I can select a subset of those and add them to a test case. So in general, what we found was presenting this information graphically was way better than you know, producing logs and things that the user would then have to post-process. So not only on the output side can we see what happened graphically, but on the input side we can cause inputs to change graphically also. So we'll just ignore these top two signals. They're kind of configuration, like setting up, calibrating a system before we start. We can just ignore those ones for now, and we'll look at these signals. And if I want to just start creating this test case again, I can select all those signals and clear the patterns on them. So now you can see we've got this test case has a duration of 25 seconds, and on the 3 inputs during those 25 seconds nothing happens. On the 5 outputs, these are expectations. At the moment we've got no expectation of what's going to happen. And you know, as I said, we've got different kinds of signals, so I've kept this one kind of simple with just discrete inputs, true-false inputs, and true-false outputs, and then we'll look at this message as time goes on. So then, and based on the information in the signal dictionary, you know, if I mouse over this icon, I can see that it's a discrete signal, and the editor here for changing that signal now is based on its type. So it knows it's a true-false and can only accept 2 states. So when I click it, it gives me a change of state of that signal. And then when I drag one side of it, I can extend that signal there. I'll just show you another way that we can edit that. So we can change the shape of this signal in a few ways, but if I go view transition list, and it's specified on the left turn switch, we see that it starts off at off, at 5 seconds it switches on, and at 15 seconds it switches off again. If I wanted to say at 16 seconds, switch it on again, when I hit the enter button, we get another change there. And then, if I didn't want 16, but I wanted, for example, 16.001, we won't quite be able to see that over on the graphic because it's not zoomed enough. But and if I did zoom down, we would see it, and you can see the value there, 16.001. So if we're driving a high resolution bench tester which can achieve this kind of value, then it can certainly be defined in the test case. So sometimes it's fine to just draw what's happening, and sometimes we might data enter it like we're working in Excel or something, and other times we might write a little equation or something for it in C code, and that way we've got several ways of defining waveforms. So anyway, we'll keep it simple for now. True at 5, off at 15. And now for it to be a test, I have to expect something and then see whether it matches what I expect. So for now, I've set the partitioning, the snap grid up, so it just matches what I'm looking for. And that might not always be the case, but certainly over here, I could then come back in and say at 7 seconds, I want a value of 1, and kind of continue the data entry mode. Or I could write an equation for this, and we can look at that in a little bit, how I would define the equation. But we'll leave it just like that for now. And my system under test, I'll see if I can bring it up here, is this guy. So it's our virtual microcontroller, another component of the suite of tools we have, and it's a separate program. And the test tool and this program communicate with a protocol called MxSuite, and what we describe that as a streaming test data protocol. So we've got the test tool feeding this test data, and this capturing results and feeding them back to the test tool. And so, whether we're working solely in a PC environment or communicating with Simulink, where we're testing a Simulink model, or communicating with a bench tester like from National Instruments or DSpace, MxSuite is always a background protocol that moves test data from one side to the other. And it does other things like manages synchronization of the two programs, so that, in this case anyway, 1 second forward in the test tool has to match 1 second forward in the system under test. And so, they'll move forward in time at the same rate. And we can either speed it up or slow it down, but they'll always move forward in time together. So that's the system under test. So I'm going to hit the run button now and see how the system under test responds to that stimulus. So I hit the run button, and we see we've got a behavior on these signals here. So I'll just expand it a bit. So we can see then this signal, the front, so I put on the turn switch, the left front and the left rear both responded, which is good. And if I look at the actual data numerically here, we can see the times it changed at. So we can see graphically, and we can see numerically, and we can see the times are precise. So, by examining this, the list and the graphic, I can decide whether what happened was correct or not. There is the possibility to have tolerances here. So when I'm running against C code or a model, it's always going to be precise. When I'm running on a bench tester, I can apply tolerances and allow some leeway on whether it passes or not. But certainly when I'm running against C code and I see a pattern that's correct, you see on the right it says fail, fail, and you can see that marker there and a marker there, but there's no markers here. So what it's saying is that the first prediction was correct. Everything else here, I didn't predict what was going to happen, and so we got failure marks all the way across there, and we got failure marks all on this one. But if the pattern's good and I see it's good, I go here, I say capture the pattern, the two patterns match, the marks disappeared and the failure disappeared, and like on this one, then we select that signal, we capture the result, and now the patterns match and it's a passing test case. If I rewind now, you can see I've got a stimulus and I've got an expectation, and if I run again then, the two patterns match, and the comparison algorithm decides they're a good match, and it's a passing test case. So that, if you like, is the simple 101 version of the test case, with discrete inputs, discrete outputs, and just a kind of no logic or any in there. It's a short duration test. So I'll just make it a bit more complex now. So I'll rewind and we'll bring in and look at what a message might look like. And to do that, we switch on hazard. So I'm going to switch on hazard here and leave hazard on for a while. So I'm going to rewind. By rewound, I'm going to clean these out because we're changing the test. So I shift click, clear that. And for now, then I mean, if I was reading the specification and I knew what should happen, then I could draw the behaviors expected. If I've just written this code and I know in my head what it's going to do, or even if I've read a very rapid way to produce test cases for checking into some automated regression test system is to do what I do, where I run the system, audit the results, and if it does the right thing, then I capture the behavior. So a few things happened here. So we can see this looks, again, correct. That looks unusual. We'll come back to that. The right turned on when hazard came on. So when hazard came on, all four were flashing and all four went off. That looks correct. Here, when hazard came on, we got a message, and we can see more on that down there. When hazard went off, we got another message, so we'll look at that in some more detail. But for now, we'll say, we'll just pick up those two, which is a control click, and say that those two are good patterns, and so I capture the patterns. And now, the only worry on that one, it's very apparent something unusual happened there, was to keep these in phase of flashing down here, I had to either extend the pulse here or delay this pulse here. And so obviously there's a systems engineering question of which way to make that work. And the way this has been implemented was to extend that pulse so that they stay in phase here. So we'll say that was the way it should be as well. So I can control click and capture that pattern. And now those four signals are all passing. And if I just look at the actual data on this CAN message, we can see, well, it's only really test data up here, nothing in particular. But if we knew that that was the right data, just like on the other signals, then we can capture that and say, well, the message is good, and now we've got a fully passing test case. But the system is aware, and can be aware for a CAN bus or a LIN bus or other data going over other buses. It can be aware of the signal information inside a message, and so if I come back to my signal dictionary and look at the output signals on the CAN bus, we see the message is already over here, but I'm going to add a new value to the test case here. And it's an analog value, so I'm going to stretch it down, and we can see at the moment it's high, and we have to rerun the test because we just added a new values, so it hasn't really got any data points yet. So I'm going to rewind and hit run again. And now we see a couple of things here. So the first 4 signals all passed again, message passed again. Here the value which came out of that message, we had no data for that value up until this point. Then we had a data point through to here. Then we had a second value through to here. So, I mean, just like before now, I can examine the value at that point and that point, and we understand that there was no message, so there was no value until that point. So I can select that signal, capture that value, and again, we've got a fully passing test case. So we introduced a few things there. We started looking at messages. We started looking at more continuously variable signals, although this one is integer based. So, you know, based on how it was defined in the signal dictionary, it came in as an integer, so it's discrete values. But it's somewhat more complex, and I just want to then save this off and we'll see what it looks like. So if I hit the save button and come here and say export to a CSV file, we can look at the data is actually stored in XML on disk, and it's quite readable in XML, but here it is. This is what it would look like if we just saved it off as a CSV file. So we can see on the left-hand side, then we've got time axis. We've got our 1s and 0s, and the message, we can see the message there. And you know, many organizations, when they start off, will try and automate by putting the information into Excel. But you can see here, managing the data in Excel is a lot worse, and understanding behaviors in Excel is a lot worse than coming over here and seeing how the system behaves graphically. So having the data immediately presented, as opposed to all that processing you've got to do to make it apparent here, it's way easier to be testing in this domain. And just another, for example, suppose I wanted to, I'll rewind, I'll select all those, I'll put the cursor here, for example, select all my signals, shift click, and I can insert time here. And for example, then put another pulse in here. Suppose that was my next test case. Doesn't make much sense, but if that was my next test case, that was easy enough to edit here. It took me you know, about 10 seconds, if that. I can hit the run button, and you know, we get our new behavior. We can examine the actual behavior everywhere here, and if we like the look of it, just like before, we shift click and accept, and we've got a passing test case. And imagine now if we did try to do the same thing here and reconstruct that test, you know, where I had extended and put in an extra transition. In this domain, you could at least spend 30 minutes trying to make that test right, and you know, it would be a lot harder to prove that you've done what you thought you were going to do over here. And here it's so easy. And you know, when we look at how people test, many people will test exactly this way by trying to use CSV files or some tabulated format. Other people will try to write Python code or some other. You know, imagine trying to recreate this test case programmatically would be a nightmare, and the maintenance on it. You know, again, if I just do something like extend, I know, extend this back here and say rewind run. And then say, all right, that looks like it did the right thing. So I shift click here, and if it, you know, and capture the behavior. If I was doing that programmatically, you know, and I'm reading someone else's code, it could take me, you know, easy an hour or something to figure it all out and be sure I had it right. Here, the maintenance, it just demonstrates that the maintenance on test cases, which is an important part of that development, the cost of development, is way easier when you can deal with the data this way. So, and I understand that not every test case, but certainly when you've got documented requirements, many of the test cases will be of the form, put the system in a state. When it's in that state, if you manipulate the inputs in this way, the outputs have to do this thing. So you know, our philosophy, I'll just switch over here and look, you see there's test cases here. We'll have really two styles of test case. One test case to put the system in a state or transition it from one state to another state, like from off to on or from engine running to engine off, whatever the state transitions are. So one class of test case will be to move the system around its state machine, and the other class of test case will be to verify that when it's in that state and I manipulate the inputs, then I expect this behavior. So we can go a long way without writing any code. We do end up in the situation where someone might say, all right, that was good, but I want to do this test case for every start time of this signal here from 2.5 seconds to 7.5 seconds. I want to vary it by 1 millisecond. I don't want to draw all those pictures. So we can look at how we can add code then to manipulate the diagrams, if you like, on the fly, but we still see everything graphically, so we can see what's going on. So we'll come to how code interacts with these diagrams in a little bit. By the way, we had a bus monitor, what we call a bus monitor here, and as things run, we can see the messages scroll by. So these are kind of canned messages. Our virtual microcontroller, this guy has any number of CAN buses, and they can communicate with, for example, vector devices or other CAN transceivers. So we could actually put our virtual microcontroller on the same bus as a real microcontroller, bearing in mind that there might not be the timing that's going to work, but on body systems it could well work. On infotainment systems it can work, and we can configure the test tool or the virtual microcontroller on a real CAN bus and start running test cases from a CAN bus and having closed loop testing and that kind of thing. So next I just wanted to bring up another test case. So as I said here, we end up with different kinds of test cases, things that move us from one state or things that prove a behavior, and the way you manage what runs next is in this thing we call a test scenario. So here we end up with some flexibility in a test scenario of how we can order things. So here I say, preconditions define the order. Things can run simultaneously or in sequence, and I can loop them. So this one I loop forever. I can change this one and say run it 2 or 5 or 10 or whatever number of times. So I can generate simple sequences here. And again, through a user interface, it's easy to generate simple sequences, but that is in many cases, and we can revert back to source code and do more complex things with this sequencing. If the graphic interface here doesn't give us the capability we're looking for. Let's see, we just looked at turn, and now we're going to look at door. So really the main new thing about this test case is that it has tolerances in it. So let me just construct this one from the start. So we'll clear out and say, and rewind and say that, well, that will work when I switch on, when I open the door, control click, the dome lamp's going to come on instantly, and then some point in time after the door closes, the dome lamp goes out. So this test case is 25 seconds long, and that I read this in the specification. This has said what it should do, and you can see there's a tolerance band around this, which is that green band. So let's just see how that works. So again, if we're running against a model, we'd expect a perfect behavior. In this case, I'm running against my C code, so it should be identical, but I could be running against hardware, in which case a mismatch would be allowed. So you see here the actual behavior stayed inside the tolerance band, and even though you can see they don't match, it actually remained passive. Just like before, if I think my system is correct and my test case is wrong, I can capture the pattern, and now I've got identical lines, and a very quick way to maintain your test cases. I can do an undo there with Control Z. If the programmer encoded this wrongly, and it should have followed the red line here. This is a very good way to communicate to the developer how he's got to change his system. I mean, all the logs are there, all the measurements are there. We can provide the whole environment to his desktop, but even just with this graphic, you can see that he got something wrong. The slope was wrong, and the delay before he started decaying was wrong as well. So it's either the test case is wrong, the developer is wrong, or possibly, you know, the tolerance band, maybe it's too wide and it shouldn't have passed. So I can go to my properties here, and it's pass fail, it's on the time, and you see I've allowed 2 seconds. Sounds like a lot, so I'm going to change that to 0.25 seconds. And now you see the tolerance band got narrower. The 2 lines didn't change, but it's now a failing test case. And so, you know, that was the third option, that just you've got to get the tolerances right before you accept that it's passing or failing. So one more example on this from this test case, and it's not a very good one. And you know, if people are interested, we can certainly do another web presentation on this. But if I look at actual data here, you can see, as I say, it's not a very good one, but you can see there's an image down here, and if I zoom on this test case, you can see that like every time we or I think every 10th of a second, the system creates a new image, and we capture that image in that events there. And if we mouse over the event, and they actually just change minusculely or very slightly between one and the other. But each one of those is available. You can see it kind of scrolls there as I move the mouse across. Anyway, you can't see very well. But, you know, sometimes when we're testing body modules and there's a user interface, then we can snap of the user interface, which could be, you know, whatever size image. You know, we've managed large images quite easily under, you know, Windows 10. We snap an image, and then we can do a pixel by pixel compare here, saying, does the one image identical to the other image? And if they're not, then we can say, well, show me the differences, and you can maybe see where on the image between the reference image and the actual image. So here, just like before, if I examine an image and it's the correct image, I can capture the image and it becomes the reference image. And now in future, if the reference image and the actual image don't match, then it will fail just like before. And that case is if we're able to get a pixel accurate representation of that image, and we can do the comparison by comparing the pixels. If we're using a camera, then, you know, we can't do that. The images won't be that identical, but we've got a nice integration with a recognition engine, which will then compare an image taken with a camera with a reference image taken with a camera, and we're able to do the pass-fail analysis separately there. All right, so we've looked at discrete signals, continuous signals, message signals, image data. As I said, this one isn't a very good example. And we've looked at tolerances. So just from the point of view of, you know, managing and executing sequences of tests, then we looked at the scenario where we can group things simply together, saying 1, 2, 3, 4, 5 in order, and some flexibility, saying what to run next after this one. So the next example will be to look at how programmatically we can control some of the test cases. So, and this has been very state machine kind of output body module, and, you know, many systems are kind of dynamic control systems, and we have you know, dynamic responses with filters and you know, integrators and that kind of thing, where we need to see the systems behaving correctly. Just one more thing while we're here. So we saw a scenario is the atomic entity that we execute. So test cases don't just run by themselves. We put them in the context of a scenario. You can have one test case in a scenario, that's no problem. And then if I go back to my Project Explorer, we see we have test cases, we have scenarios. This one's an interesting one. Let me just bring up one of those. So you know, not only can I run these test cases predefined, but I can have control of the signals, you know, with my mouse. So I can just experiment on my system, saying what happens if I do this, or what happens if I take the vehicle speed and increase it or decrease it, that kind of thing. And you know, I didn't run this, but if I ran that, I have to make sure these test cases weren't doing anything at the same time. Then I can experiment with my system, because I've got access to all the same input-output signals, and automatically, you know, we don't have to build this panel. Just based on the type again of the signal, we give you a control that allows you to manipulate that signal. Regression is really a way of packaging up all your test cases, or many of your test cases, a subset of your test cases, to run in an automated fashion. You know, often we're going to do that as a, you know, prior to a release of a system, to run a large portion of our tests, or maybe I've just changed some subsystem and I want to run all the tests for that subsystem, or maybe, you know, on an automated agile environment, maybe we just say every time someone checks in a file, we run a regression test to say that it still builds and it still passes all the tests that it used to pass. So we could look at that. You know, if there's any questions, I'll leave some time. But the one other project I wanted to look at before I finish, and maybe have some questions, is a more dynamic system. So I'll go to recent projects. This one, which has some Simulink component. So we're running in a closed loop fashion. So it is, maybe see at the bottom of my screen, it just launched Simulink, and the demo isn't really of Simulink, it's still of the test tool, but it does show that we can test Simulink models as well as just testing on our virtual microcontroller. And you know, one of the things with you know, code generators, you know, I don't know if it's changing, but you know, it's a difficult problem formally validating a code generator, which means you've got to do your testing downstream of the generation. Now, if you're doing a lot of development and testing on Simulink, then the ability to use those test cases on the Simulink model ahead of time, and then on the generated code after you've done the generation, saves a heck of a lot of development work in being able to test early and test after the generator's done its work, and prove that the two systems are equivalent. And as I say, one of my colleagues will be going a bit more on that in a couple of weeks when he demonstrates with testing on the target. All right, so in this one, this project here, you can see some of the curves are more curvy. We've got some things happening in our scenario. So ignoring the first two, and they're really something we do just because we're running software in the loop. So they're not really part. The initialization gets our system under test ready. This gives, if you like, a real-time interrupt to our to the system we're testing, to our virtual microcontroller, which, by the way, is I think it's every 5 milliseconds. So what we're going to do in this sequence is we're going to get into this desired initial state, which is accelerating to 50 miles an hour. We're going to think, and this is the vehicle's cruise control, you know, speed hold, non-adaptive. We're going to engage and disengage the speed hold, and then we're going to re-accelerate to 50 miles an hour, and then we've got this thing called uphill, down, dale. So we've got the sequence of 4 things there. So we'll look at this one first, accelerate to 50 miles an hour, and we'll come back to the other ones. So first, if I hit the run button, now, there we go. You can see we got curves. This is an input signal, it tells me, and this is an output signal. but both of them were calculated. So now, in the past, the input signals had always been predefined, and in this case, the input signal was calculated, which is different. And that's because if I've got a model of my system which is controlling the speed of the vehicle, and I start off with the vehicle at 0 miles per hour or kilometers per hour, ahead of time, it's hard for me to know how much time I need to spend with my foot on the gas and get to the speed. So we calculated this, and we can see, I think in there it is. So this test case, you can imagine it like a little controller of its own, a little real-time controller of its own, and it's got a tick, like a real-time interrupt, even though it's just a simulated PC environment. But you can see that with those 5 lines of code there, really, I was able to calculate an error in speed. So the target speed was 50. The actual speed, which is this guy, was whatever the vehicle's going at. I got a delta seed. I created a proportional term and an integral term, and calculated a pedal percent based on those values. And then just these 2 lines said, well, I can't have more than 100% and I can't have less than 0%. So I'm going to clamp it at those values. So with those 5 lines of code and a target speed of 50, we can see that as soon as I started the test, we got to 100%. And then, so we put our foot to the floor, the vehicle started accelerating at its maximum rate. And as the error in speed decreased, I backed off with my foot until my foot steadied out at 5.12%, and my speed honed in at 50.0. So that was, we tweaked those gains a bit, but we certainly, in a time duration of 30 seconds, were able to get the vehicle to a certain speed programmatically, instead of, and the alternative would have been to draw maybe 100% pedal position for 5.44 seconds might have got me to 100, and I could have predefined it. But this way I was able to use a piece of logic and code to say what happens in the test to get to that speed. So we can see this much more dynamic system. Let me just switch out and show you how Simulink is involved here then. So, we've got Simulink running. Well, let me click here. So this is a viewer that a component of the tool that shows us logical view of the system we're testing. So you can read this diagram a bit like you'd read a Simulink diagram. So we've got three blocks of interest in here. We've got the algorithm. That's the piece of code we're testing. This is the piece that's going to go in the embedded controller, which takes in a vehicle speed, and it takes in this toggle switch, which engages or disengages. So this is able to lock onto a speed, and based on then the error in speed, gives us a position of the pedal. This one here says the driver can override that pedal position, or we can take the algorithm pedal position. This one is a model of the engine, kind of trivial, but just says if I have so much pedal position, I end up with a drive force on the engine. And this one here says if I end up with a drive force on the engine, I'm going to end up with a certain vehicle speed. The vehicle model was in meters per second. The algorithm was working in miles per hour, so we just convert it there. We end up going in miles per hour here, and so we've got a closed loop environment. So in fact, we're testing this piece here, which is Simulink, but it's more a demonstration of the test tool. If I'd written that and put it in my VMC virtual microcontroller, I could, which is the one I was using before, I could drop this in here. There's a few steps to do, but I could make this encapsulate a piece of code that would be generated from here in here, and then replace that one with that one, and now I could be testing C code instead of Simulink model. So anyway, that's the system under test there. We'll switch back to the test tool, and we'll put that one away. So we can see that this one gets us to 50 miles an hour, and then the engage disengage It's often easiest to look at this one, so I'll just rewind and look at it slowly. I'm going to put a breakpoint in the test, a breakpoint in the test case here. So we're going to hit the run button, and you can see we started off at 50 miles an hour. We started coasting down because we just took our foot off the gas. This is the engage. So as it's coasting down, I'm going to run this. We engage here and we disengage here, and you can see this is how we expect it to go, because this is what it did last time. So if I run it slowly, so this just changes the speed of the whole simulation, and hit the run button. Now we can see it happening. It engaged here. It oscillates a bit. With just an up and a down, seems to acquire the speed. We hit the button again, and it coasts down again to the end of the test case. So, you know, if I was the systems engineer with some experience, I'd know whether this was an acceptable kind of shape, or whether you know, it needed tweaking, the control algorithm needed tweaking, or I might give my algorithm to a rapid prototyping test driver, and he would run the same thing in his, and you know, we could run this in the vehicle on a D-Space micro auto box and capture the same information, and someone at some point decides that this is acceptable, and then we can set up our tolerance band, build a tolerance band around that shape. So we'd say in the modeling world we want it to be precise, and on the bench tester, as long as it stays in the envelope, then we're going to say it's acceptable. Just like before, you know, this is a very predefined sequence, but we can, I don't think there is any in there. Yeah, there is. So you can see that even though this is a simple sequence, which I constructed through the user interface, it's actually got some code behind it that is going through that, essentially saying when this one's done, do this, when this one's done, do this. So you can switch over and start editing that code and come up with as complex a sequence as you like here. So now, if you like, we've switched away from using this to do the sequencing, and now a programmer can go in and you know, if they want to make this as complex as whatever, they've got the full ability to control that order of execution, instead of just being confined to using the simple sequences that we can do this, which is run things and repeat counts and maybe run things concurrently. So I think I'll just mention one more thing then. In the virtual microcontroller, you know, there's a bit of a technique to attaching the test tool or attaching MxNet to the code we're going to test. In some cases, we can automate it. So, for example, with Simulink, it's a very well-defined interface, and we can pretty much attach the test tool to a Simulink model automatically. With AutoSAR code, the interfaces are defined by XML definition files, AR XML files. We're able to parse those and automatically connect the test tool to AutoSAR code. And in the works, and I could probably demonstrate this in a couple of weeks, we have got a parsing capability that's able to analyze source code and tell us what the entry points, the function calls are, the global variables are, the parameters are, and automatically connect to that source code. So it's a prototype now, but it's making rapid progress. We could probably demonstrate that in a couple of, you know, 2 or 3 weeks. So you know, there's always the question of how you attach to the system you're testing, and you know, we see that as a big benefit to be able to automate that attachment in every case possible. And even for the bench testers, like with National Instruments, Veristand, and D-Space, we've got a high degree of automation in connecting the test tool to that test environment. So I think that's my 101 introduction. Have you got any questions from anyone?
So if you have questions, just fill out in the chat window your questions. I haven't received any so far, Mike.
All right.
so I think we had a pretty low attendance
Oh well.
today, but I thank everyone for joining, and in 2 weeks we will repeat the session with MxSuite, but focusing on how we can use processor in the loop, hardware in the loop, in particular using a Lauterbach debugger for processor in the loop testing. So very many thanks to you, Mike. I have recorded this presentation, and we will put it on our web, and we will distribute the link to everyone that's attended.
Sounds good.
Okay.
All right. Thanks, Sam.
Have a good day now.
Yeah, bye.